Welcome to my presentation. My name is Omar César Díaz Lobatón, a student at the Toluca Institute of Technology, part of the National Technological Institute of Mexico, working under the guidance of Dr. Celso Hernández Tenorio, Hilda Moreno Saavedra, and Claudia Cortés Escobedo. My research topic is the simulation of a PEMFC-type fuel cell using SIMULINK. To begin with, a PEMFC is a proton exchange membrane fuel cell. This type of cell is significant due to its high energy efficiency, low pollutant emissions, and ability to operate at moderate temperatures. However, conducting experimental studies on a fuel cell can require a considerable amount of time and resources. For this reason, mathematical modeling offers an alternative for studying and predicting the cell's behavior under various operating conditions. In our work, we developed a dynamic mathematical model of a PEMFC membrane. The model accounts for various phenomena occurring within the cell, primarily electrochemical, electrical, and thermal processes, as well as gas transport. Additionally, a sensitivity analysis is performed to identify the parameters that most significantly influence the cell's behavior. Electrochemical principles. We will now briefly explain the electrochemical operation of the PEMFC. The overall cell reaction can be expressed as, in general terms, hydrogen and oxygen react to produce water, simultaneously generating electrical energy and heat. The Nernst equation is used to determine the cell's reversible potential. In this model, the equation primarily takes into account the temperature and the partial pressures of hydrogen and oxygen. However, the actual voltage of a PEMFC does not simply correspond to the reversible potential, as various losses occur during operation. This model considers three main types of losses: activation losses, ohmic losses, and concentration losses. Therefore, the total cell voltage is expressed as the potential derived from the Nernst equation minus these three losses. That is, voltage equals Nernst equation minus activation voltage minus ohmic voltage minus concentration voltage. This equation is fundamental because it allows for a more realistic representation of the cell's voltage behavior as the current changes. Mathematical modeling and implementation. Continuing with the work, the mathematical model is divided into different submodels. First is the electrochemical submodel, which allows for the calculation of voltage by accounting for the reversible potential and electrochemical losses. Next is the electrical submodel, used to calculate the generated power. This is obtained by multiplying voltage by current. A thermal submodel is also incorporated, establishing an energy balance between the heat generated during operation and the heat dissipated. Another important component is the pressure submodel. In this case, hydrogen and oxygen pressures are calculated using the ideal gas law while accounting for the stoichiometric consumption associated with the current. Once these models are established, they are implemented in SIMULINK. Implementation begins by defining the physical parameters, followed by the integration of the electrochemical, thermal, and pressure submodels. Finally, the explicit Euler method is used to perform numerical integration, enabling the observation of variables such as voltage, current, power, and temperature. Sensitivity analysis and the membrane sensitivity analysis is a key part of our work. To conduct this analysis, we adopted a methodology based on the work of Correa et al., in which various model parameters are modified within specific ranges, and the resulting effects on output voltage are observed. The results allow the parameters to be classified according to their level of sensitivity. Parameters considered highly sensitive include maximum current density, activation coefficients, and parameters related to concentration losses. Internal current and transport coefficients are considered moderately sensitive parameters. Finally, parameters with low sensitivity include active area, membrane thickness, and contact resistance. This is important because it identifies which parameters should be the primary focus of model calibration and optimization effort. Finally, the developed model enables the generation of various results that allow for the analysis of PEMFC performance. These include polarization curves, power density curves, temperature evolution, and hydrogen consumption. It is also possible to study the influence of carbon nanotube concentration on the cell's behavior. A key finding from the sensitivity analysis is that small variations in certain electrochemical parameters can lead to significant changes in voltage prediction. For this reason, the study highlights the importance of performing experimental calibration for each specific membrane formulation. In conclusion, the developed model serves as a tool for analyzing and optimizing PEMFC-type proton exchange membrane. The combination of dynamic modeling, implementation in SIMULINK, and sensitivity analysis makes it possible to identify critical parameters that influence the cell's electrochemical performance. Thus, the model can support the study of different operating conditions and guide future stages of experimental optimization. Thank you for your attention. I am grateful for the unconditional support of my advisor, PhD Celso Hernández Tenorio, my co-advisor, PhD Claudia Alicia Cortés Escobedo, and my professor, PhD Hilda Moreno Saavedra.